there's swag afterwards, so like hit me up. I want to talk about something a lot different than we've been hearing for most of today. John, please, now for something completely different. First, I'll talk a little bit about me. My first paying gig was in '78. I did some Apple II software for FEMA, and I actually got flown down to Washington and got to see DARPANET in the FEMA Communications Center back in '79. And you know, the internet's come a long way since then. I'm not traditionally trained in computer science. I've got a double degree in psychology and economics. I'm a lawyer, yeah, boo. But I've been doing technology ever since, well, professionally since '78. I wrote the first real-time spreadsheet, first server-based spreadsheet, and I've been through the Java thing since '96, and I'm starting to see patterns, and I'm starting to see echoes of the past. One of the things I did 10 years ago was found a web framework based on Scala called Lift, and helped evangelize Scala back when it was just a purely academic language. And you know, went to places like this and said, dump your Java, type systems are great. And some people did, I'm sorry. But what I've come to realize in the last decade is moving like large groups of developers to something new is a really, really hard process. And looking at the stakeholders as we kind of look at enterprise development, and you know, we have 500 billion annual reasons to care about the enterprise. We have a bunch of drivers, and one of the most interesting drivers that started kind of coming on my radar about a year ago was CEOs caring about digital transformation. So CEOs are now, you know, telling their board and telling their investors, we're doing a digital transformation, we're becoming a digital company. And you know, it's a more polite way of saying software is eating the world. And the way that CIOs and CTOs are expressing this is cloud native. So, okay, how are our apps becoming cloud native? And for the chief financial officer or general counsel, they care about compliance. And as we start going to the cloud and as our data is resident on servers someplace and storage someplace, how do they guarantee compliance? And compliance is really important, especially if you're in finance, if you're in medical, if you're doing business in Germany or France. There are a lot of compliance issues. Engineering management wants forward progress metrics. And it's really super important for them to show forward progress towards the strategic goals of the organization. So, you know, it's like Agile actually was the first way, the first standardized way of doing these forward progress metrics. And finally, engineers want well-defined success, shiny things, resume enhancement, and a bunch of other stuff. So we're on a waypoint of a journey, and ultimately we have these monoliths, we have these legacies, we have these mudballs that need shaving down, that need to move to cloud native. So how did we get here? Let me tell you a story. It started in the 1960s and 70s with the IBM 360. We actually had a beautiful concurrency mechanism back then. It was called ACID. It was called the relational database. And basically, the relational database was a clear separation between the semantics of the business logic and the guarantees of concurrency. But systems were mostly isolated. In other words, the inter-IBM 360 communication was very rare. But the database was the coordinator of the distributed system. And what happened between begin transaction and commit was up to the app developer. What happened after commit was up to the database developer. And there was that clear separation. There was a clear division of responsibilities. So at the end of the day, the application developer did not need to roll their own concurrency guarantees. But we also saw Brooks with the Mythical Man Month identifying people problems. And a lot of what happened that led us to where we are today came from military structures, because ultimately the military was the most successful large-scale collection of people, and a lot of our infrastructure, a lot of our ways of doing business reflected that. But at the end of the day, you had folks down here, engineers down here who needed to communicate. and their cost of communication was either going up and over, or having this incredible mess of like ad hoc communication channels. And we saw that reflected in waterfall. And ultimately, you have a problem that the cost of communication among those nodes is very high, and the cost of not communication is very high. Additionally, we had slow cycle times and expensive IT budgets, and that ultimately begat VisiCalc, which begat the PC, which begat 123, which begat Excel, which is now the most popular programming language in the world. Basically, people who don't self-identify as programmers use Excel. They write in a Turing-complete language. They express business logic. And one of the other interesting things was the exchange of floppy disks in the 70s and 80s with 123 or VisiCalc models was actually an early indication of open source. So we moved to the 80s and 90s with client server. We basically moved the computation logic from the mainframe up here. We still have the database as a coordinator. Maybe a little bit of Corba, which is trying to replicate an in-process call across a distributed network, but anybody who's used Corba, well, hates it. So three things happened at the same time, and I will argue that all three of these things were a radical reaction to internode communication costs. The first was the World Wide Web. So about 20 years after DARPANET, we had the web, and the web fundamentally changed the way that everybody communicates in the world. We also had open source. So rather than having top-down militaristic structures for standards committees, we basically had people who built software, garnered community around the software, and that became the standard itself. It was also a reaction to some antitrust laws so that IBM couldn't really participate easily without going through a lot of antitrust stuff, but they were able to collaborate on open source projects. And finally, XP was our first true reaction to the militaristic structure, to say, okay, we're going to create these small ways for people to communicate, for developers to communicate and be efficient. So we have web apps from the 90s and early 2000s, and they seem similar. They actually, we have our 3270s, our browsers up here. We have our business logic hosted in on servers. We have maybe a couple of databases rather than just one, so maybe some distributed transactions. And some small communication via RMI or other things out to external systems, but it really didn't work or feel right. But in the mid-90s, all of a sudden the communication or the computation capabilities of the browser became enough that we could actually push logic, not just simply rendering, but actual logic to the browsers. And we got REST, we got JSON, we got jQuery. And further, we got Rails, which was ultimately a backlash to the complexity of Java. And Agile was becoming mainstream. So then something happened, or two things happened in 2007. The iPhone landed and AWS landed. And that, in my mind, has been the largest shift in computing in my lifetime, which goes back to the IBM 360. Basically, the world as we know it changed. And 10 years later, we're finally making sense of the change that both of those things brought to us. The internet being everywhere and servers defined with lines of code rather than with physical cables. So on the cloud side, we finally, I think, gotten to the correct level of granularity. We've gotten microservices and we've got serverless. Serverless is the deployment mechanism for microservices. Microservices are a rational way of defining a chunk of software. And we have the correct packaging, which is containers. I mean, quite frankly, in my mind, containers are the same thing as war files. You basically take all your dependencies, put them in a single place, and upload them, and you package once, they run everywhere. But we still have this insane complexity of web and mobile and how many front-end platforms do you use? What services do you choose to use? What services do you choose to implement yourself? What are the security ramifications of having your data traverse different servers with different guarantees? Web scale. Where do you host? I mean, there's just like, which cloud provider? Do you go multi-cloud? Do you have an built-in cloud? These are all like really hard problems. But I think serverless is giving us a way of kind of bounding those problems by adding constraints. and giving us answers, which is, okay, we bound the business logic to a small unit. We can host that small unit in predictable places without actually worrying about the physical hardware that they're running on. And they communicate via events. But we have this hidden problem. Our transactional guarantee is lost. That piece that we did where we could basically do everything between begin transaction and commit, we no longer have. And every developer effectively has to roll their own distributed logic. And how do we do this? We copy and paste code from Stack Overflow. So, when you hear just break it up into microservices, what you're hearing is copy a lot of distributed logic code from Stack Overflow and pray the stuff works right. So the monolith actually has a series of advantages. The stuff all in one memory space is much easier to test. You can test your whole system. You don't have to fire up 40 services. You don't have to figure out how to mock them out. You can just use the existing tests. It's a pattern that's been ingrained in us for 50 years. And so we're repeating the same pattern. Breaking a pattern is extraordinarily difficult. And yes, there are deployment advantages, and there's some coding advantages for smaller projects around functions. But how do you basically drive those advantages to companies that ultimately know what the downside of their monolith is, but don't know what the upside is? And you're looking at a map where there would be dragons. It's like, okay, we don't know what's there. And anybody who is in corporate America is going to go, okay, I'm going to go with the known pain rather than the unknown pain, even if there's potential gain there. So I'm here to talk about Funkatron, and I think about it as the last mile of business value delivery. How do you basically deliver on top of all of this cloud-native infrastructure, the containers, the container orchestration mechanisms, the local clouds, the public clouds? How do you do that? So Funkatron is a serverless deployment platform with tooling and playbook to help shave monoliths, help shave the mudball down into manageable services, with metrics and goodies to satisfy upper level management. So we can not just say, we're going to do this, but we give measurements so that over time you can sit down and say, we've done X in the last couple of months. So what are some of the drivers and philosophies? Our logo is an ant, because ants have a series of simple signals that allow the orchestration of very complex behaviors. And if we take a look at Agile, Agile is a bunch of simple signals that we give to each other every day. We can all drunk at 3 a.m. If somebody wakes you up, it's like, what do you do in Agile? Stand up, costing, end of sprint, sprint planning, product owner. I mean, great. Everybody can recite that. It's a series of simple signals. We need to do the same thing as we break up our monoliths into microservices and deploy them on serverless. We want to focus on the business logic. Ultimately, with Funkatron, we want to meet existing developers where they are. And this is a mistake that I learned from doing Scala evangelism. You're not going to, no matter how beautiful a type system is, you're not going to get people, the broad part of the normal distribution of developers, to think about type systems. They don't want to study for 4 years before they can churn out code. So we want to meet the developers where they are, but we want to take some of the good research that's going on right now into distributed systems and make that palatable, understandable for the developers. We want to use existing tooling, but add small steps where there's a defined, well-understood reward at each step. So I think about it as Reese's Pieces from E.T. It's like, when the kid wanted E.T. to follow a path, he put down Reese's Pieces. The alien, E.T., got a reward at every step. And ultimately, that's what we need to do to bring corporate developers who are used to the monolith into the land of serverless. And finally, for Funkatron, for the company, we're focusing on large-scale projects with legacy code. So rather than saying, hey, let's run off and build this greenfield project, we're saying, hey, you've got a ball of mud, let us help you with that. And it's quite frankly a financial decision because there's a lot of money in those balls of mud. So let me actually do a quick demo. Because of the network connectivity issues, I have downloaded a Maven archetype, but if you can read the super small stuff, it's Maven generate. So basically we build a Funkatron project just from a Maven archetype. So it's something that most Java developers know how to do. We have a junior version of Funkatron running in a single container over here. And inside our IDE, we have our Hello World application. So for those of you who do functional programming, we have an apply method. And the apply method is wired into the application with basically at a certain path, the get method basically invokes a particular class. That class is then applied, hooray, our function is invoked. So Swagger is nothing new, your IDE is nothing new, most developers are familiar with Docker, that's not going to be scary, and most developers are cool with Maven. So you basically build a Maven archetype, and we go take a look at it, and boom, we have our apply method. We automatically turn the incoming request if it's got a body into the first parameter, and the context of the call is the second parameter, and then you return a value, and depending on what you return, it's serialized into JSON or a whole bunch of other stuff. So let's have some fun with this. We've set a breakpoint here, and we are going to go debug the app. Going to go into our browser and hit reload, and we have a breakpoint. Hooray. So within the breakpoint, we can go in and we can modify the value of the variable, so change it from 42 to 555. We can continue our execution, and when we go back, we get our answer as 556. So as a very simple thing, a developer can now write a serverless function that runs in Java, that is debuggable in their existing IDE. We also support taking a Spring Boot application, adding a couple of extra dependencies. We can pull the Swagger out of the Spring Boot application and host the basically allow the Spring Boot application to be auto-scaled on the Funkatron cluster. So it's a serverless deployment platform, shown you that it integrates well with existing IDEs, existing ways that people do stuff. We sit it on top of Mesos or Kubernetes. Why do we do that? It's cloud provider agnostic, but more importantly, if somebody's running their own internal cloud, we don't want to interrupt what they're doing with their internal cloud. We want to allow the investment in infrastructure to continue. And if you're running Mesos or Kubernetes, you can run it on your internal cloud, or you can run it on a public cloud provider. Deploying a Spring Boot or Swagger app, and you'll basically we support auto wiring. Let me actually go in and show you. So we hit our URL. If we go back and we stop the app, and we go back to our browser and hit reload, there's nothing defined. So once that particular app drops out of the cluster, it auto unwires the endpoints. Why is this important? If you think about a Java web application with a WAR file where you're basically your whole world is defined there, you drop it someplace and it wires up all of the endpoints correctly. That's what developers are used to. So being able to do the auto wiring and scale with the auto wiring makes deployment a lot easier. It auto scales. Even out of the box, even if you have a large system, we will basically not granularly, but on a gross level, auto scale the app. So we take a look at the number of incoming requests. We use process control, getting back to what Paul was talking about, going back to the old math. We're actually using the math of physics to choose how to scale up or scale down an application. And we have a bunch of forensics-friendly logging. So for every request that comes in, there's a UUID associated with the request. As that function is fanned out, we actually carry the UUID around, so we can either surface that in New Relic or surface it in your logs and allow you to see how a request fans out. For a monolith, not really super important, but as you start shaving the monolith down, you'll be able to see how your application, how a single function call ripples through your network. We also log the git SHA of every single request. So if you're doing a green-blue deploy, we can tell you which log line was green and which log line was blue. If 6 months from now you find out there was a breach sometime between 2 dates, we can actually tell you exactly what software, exactly what Git version was deployed at any given time for any given request. We're also working on a mudball shaving playbook. So what does that mean? We basically help enterprises make the right choices about which pieces of the application to pull off first. We then are defining certain formal contracts. So the first formal contract, and if you think about type systems, the first formal contract is Swagger. Okay, great. I can tell you what the types are and what the methods are for this application. Those are the endpoints, the request method, and then the data shapes. Great, that's nice. What else can we add to that? We can add an SLA. So what is the SLA for a particular service? How can we test the SLA for a particular service? As services are fanning out, how can we make sure that if one of the SLAs will be violated, we can fast fail? That's something of value. We are adding other things that are based on research that we are paring down and making available to Java engineers to understand a little bit more of the complexity of a distributed system. I'll get to that in a little while. But ultimately, these contracts become signals to the team. They become signals that are a combination of machine readable and also human readable. And more importantly, they are things that we can do generative tests with. And once you separate the component, you define the contract. Based on the contract definition, we generate auto tests for you. You can deploy it more confidently into a CI/CD pipeline. So let's do a checklist of where we are. We've got 16 minutes left. We've got something that runs on a clustered auto scales. Hooray, that's a benefit. We have, and I've hand waved a little bit, but we have a methodology for shaving off particular components of the mudball. We have a way for teams to give small signals to other teams or to future versions of themselves. So, you don't have to learn a lot to be able to do this. You don't have to add a lot to your repertoire. And it's standard stuff. And with generative testing, we can actually enhance your testing, and not just the happy test that a lot of people do as unit tests. Oh, I'll hit the sample URL. Hey, it gave me a 200, passes. Rather than saying, okay, here are 10 tests that should pass and 10 tests that should fail. But if you have 40 services from one monolith, how do you coordinate them? And I think that's, to a great degree, the elephant in the room for this conference, which is being able to do the greenfield wiring up 5, 10 simple functions, swapping them out, having a team that has a mind meld. That stuff all works. It's a lot like early Rails days. But you really need a way of coordinating. And we really have to answer the question, have we moved from the mudball, have we moved from the monolith to the unmanageable? Or how do apps and services talk to services? So in addition to the using Swagger and defining the SLA within the contract, there are options for doing something called SISE, which is a tool that's developed by the Sync-Free group, that if you make certain assertions about your code, the first thing that the tool will do is it will actually send your assertions to a SAT solver and tell you whether or not your assertions guarantee your invariance. So does your application actually distribute the way that you expect it to distribute? There's also some tools being developed at Cal Berkeley that fall under the category of lineage-driven fault injection. So once again, a few additional lines in the Swagger file or a few additional annotations in your code, and we're going to be able to say, okay, we can be far more brutal to this code because we've pared down the stuff that we have to inject at the test surface. You know, think about the test surface just like the attack surface. The test surface is the component's contract. You've told us a little bit more about the contract, and now we can craft malicious or potentially breaking code. So these things start giving you more comfort in having a distributed system that's going to work. The generative testing, the positive and negative tests. So it's not just a happy test, it's not just what I expect or a few negative tests, but it is stuff that is based on your contract. Let's see if we can break the contract. So ultimately, I'm calling it Funkcelerator. It was the name I came up with today. I don't know whether I like it or not, for declaring service relationships. And this goes back into a lot of the stuff that I learned in both Scala land and Haskell land, and it even goes back to my spreadsheet days. Because at the end of the day, one of the reasons that spreadsheets are so powerful is you don't have to mimic the CPU in your mind to write a spreadsheet. What you do is you define relationships among cells, and the spreadsheet application resolves the dependencies and performs the computations in the proper order. So it's no longer up to the human, it's no longer up to the writer of the algorithm to figure out how to execute it. It's up to the, because there's enough information in the spreadsheet, it's up to the spreadsheet engine. By the way, I'm going to take a quick break here. I was talking about the SCSI stuff from Sync Free. So, you know, what we have here is what? 10 annotations. The annotations are maybe a little bit non-intuitive, but they're not really scary. You know, you've probably seen a lot worse stuff in Spring Boot apps. So, you know, we basically have a series of invariants, things that must be satisfied. We have a description of some of the operations, and based on these things, the SAT solver that SCSI has will figure out whether or not the guarantees, the invariants, will hold in a distributed system. So, Funkcelerator, scatter gather. If you think about what we're going to be building inside our distributed function, our serverless code, we're basically going to take an incoming request, and rather than chaining it 1, 2, 3, we're going to send out a series of requests, and then we're going to gather the results back. It's, you know, it's a standard enterprise pattern. So you're going to send the request out to end services. Some of the answers are required. Some are optional. All the services have a contract. So we can actually figure out at development time whether there are any violations, whether there would be any potential violations of the contract. For optional answers, you might very well say, hey, here's a default value. We want to fast fail if any of the required answers come back with a failure. We also want, at an operational level, to be able to track and log the UUID and ultimately send it out to New Relic. Funkcelerator. So let's take a look at a use case of a purchase order. So, you know, you get a purchase order into your function, and what do you ultimately want to do? You want to get information about the customer. You want to map over the line items for the purchase order. You want to create the various different shipping configurations, which is a reduce. So in other words, you might say, you know, there are four items in warehouse A, 20 items in warehouse B, 6 items in warehouse C, but the next line has a certain other configuration, and you might want to create all the permutations of what you can ship. Very often for corporate stuff, you know, you're shipping batteries or chemicals, there are legal requirements that are state by state, jurisdiction by jurisdiction about what you can ship with other things. There might also be carrier requirements. So you create all of the possible permutations of shipping to satisfy the purchase order. And then you, by the way, this can be done in parallel. This operation is serial. So you basically do scatter out all of these requests, gather them back. You do a fold operation here or a reduce operation. You do a filter based on what are the valid configurations. That can be done in parallel. We do a map. We basically go out to all of the shipping partners and say, can you give me a quote for all of these? Based on the quote, we basically do another reduce operation, and we respond to the request. Now, if you wrote that in Java, I don't know, I bet it would be 50, 60 classes and probably 20,000 lines of code. Let's actually take a look at what it should look like. So we know that we want the answer to be the stuff that we shipped. And hey, you know, we've got quotes and we've got customers and all of that sort of stuff. We shouldn't have to, as programmers, think about the order of the operations. We should declare the operations that we want to perform, and the computer, the system, should be able to build a dependency graph, should know what needs to be lazily evaluated, what needs to be eagerly evaluated, what doesn't even need to be evaluated at all. Because, you know, you might get to a particular point in the computation, you can say, you know what, we know that we're not going to ship from Alaska to Maine, so we'll just like stop asking about the Alaska stuff. Or if we don't get answers back from the Alaska warehouse, we'll continue to execute. So being able to say in pseudocode, and by the way, we're going to implement this both as Fluent Java and as JavaScript. You basically make declarations, and the computer figures out what the dependency graph is, and also based on if you add attributes to your contracts to figure out whether the invariants will be satisfied or not satisfied based on the dependency graph. I believe it's composition at the right level of granularity. So, you know, once again, going back to Haskell and Scala, there's always arguments about composition, and no matter what, you wind up with these very, very trivial examples of composition. But ultimately, what we want to do is we want to compose our functions across our grid of computing. We want to compose our functions across our compute mesh rather than composing them very simply in the same address space. We need lazy evaluation because some of these things need answers immediately. Some of these things don't need answers immediately. We need the dependency graph because at some point, you know, if we go back to the militaristic structure, if the leaf nodes, if the developers have to communicate 20 groups with each other in order to coordinate, in order to figure out what the true dependency for a particular implementation is, then you're back to the monolith, even if you're deploying it in a serverless way. At dev time, having some type information but not anal type information like Scala or Haskell, having some published SLAs so you can basically say, you know what, I can sum this stuff up, and if you get a purchase order with more than 20 entries in it, I can tell you based on that on the SLAs of all the services that you're calling that you won't match the SLA that you're publishing for this particular, for the purchase order service. And constraint checking. So if you add some of the invariants and some of the descriptions of what you're doing to your code, can you basically have the system tell you, you know what, this is not correct code. Do you want to add certain other guarantees to the code? Do you want to do effectively a stop the world, synchronize all of your data stores together before continuing? You get the generative tests, but the generative tests across the cluster rather than simply the generative tests at one unit. And ultimately, at runtime, we can figure out whether the published SLAs are matching the actual SLAs. And if the published SLAs are not matching the actual SLAs, we can fast fail a percentage of the requests so that basically the system continues to operate. Because one of the things that happens with systems is when you get to the 95th percentile, if the performance problems between the 95th and 96th percentile are a lot different than the performance problems between the 40th and the 41st percentile. And what you want to do is you really want to keep the system underloaded, because once it goes into overload, there's a whole bunch of cascading failures that wind up happening. So if you can fast fail requests because you start seeing that the system as a whole is not that certain components aren't meeting their SLAs, it's going to give you better availability for your entire system. And ultimately, when you get to the end of it, when the mudball is small enough, it's manageable inside one or two teams' heads, and then you're back to the kind of development that we expect, the kind of development that we see in the first year, 18 months of a project. So at the end of the day, with Funkatron, what kind of metrics and goodies are we giving? We're deployment on Kubernetes and Mesos, it's forward progress towards cloud native. So great, the CIO can start checking that checkbox. Incremental process with dashboards. So one of the things that we're going to be offering as a commercial product is integration with Rally and some other tools to create dashboards. So as you're shaving down your mudball, as you start figuring out what components to shave off, as you start defining the contracts for the components, as you start actually shaving them off and putting them into production, we're going to give a dashboard on that so that the upper level people don't just see velocity or aggregated velocity, but they actually see incremental progress on substantive things rather than the big bang of, okay, we've got this velocity, we have this number of estimated points, so it should come out next April. There's forensic tools for compliance. And there's some cool stuff that we're doing with, once again, these are commercial editions, compliance around tools that support guarantees of geolocation of program execution and certain guarantees about supporting HIPAA or PCI data. And it starts taking us, the engineers, steps back towards the world where the database was our single source of truth and our single source of concurrency guarantees. It's not going to take us all the way back there, but there's tremendous amount of good research that's coming out of university right now, that's coming out of the research folks, that being able to package that and turn that into something that is consumable by the vast army of Java engineers, .NET engineers, Node engineers, is going to really help them. It's going to help them write correct code so that they can really focus on the business logic. So I'd like to invite all of you to join the journey to Funkatron. We've taken our first few steps. Information is available at funkatron.org. We have our stuff open in GitHub repo. We're on Twitter. By the way, I got the Twitter handle, I got the .com domain. I also got the .io domain this morning because I had forgotten to do that. But we're on Gitter for real-time chat, and that's it. So thank you for your time, and if anybody has questions, let me know.